Good morning, everybody. We will wait a couple of seconds while a few of us join, and then we'll make a start. Good morning, everybody, and welcome to Airspace of the Future introduction webinar. We're just going to give it another minute or two just while everybody joins the Zoom session, and once we've had that, we'll make a start. Good morning, everybody, and welcome to Airspace of the Future introduction webinar. I'll just give it one more minute just because I can see there's a few more people just joining us. And once we have a couple more people with us, then I will make sure we make a start. Great. Okay. We've got quite a few people with us now, and thank you very much, everybody, for making the time to join us on this webinar. This is Airspace of the Future, an introduction. It's a webinar just giving us an overview of Airspace of the Future as a project. I'd also like to, I will be making a start. My name's Courtney Newbold. I'm the lead project manager on this project. At this moment, I'd also like to introduce my technical lead on the project, Phil Vernal.
Good morning, all.
Perfect. Okay. Well, thank you everybody for joining. The place I'd like to first start is looking at the Zoom technicalities. If you ever have a question at any point during the session, please feel free to use the Q&A at the bottom panel. The panelists have visibility of this at all times, and we will be reviewing regularly. There is a session there is a space at the end of the session where we'll be addressing all these questions at that point. Also, there is a chat function, so if there's anything you want to pop in there, please feel free, but preferably pop your questions in the Q&A and we'll address them at the end of the session. So without further ado, let's make a start on this webinar. Next slide, please. Within this event, we're going to introduce you to what is Airspace of the Future, looking at the problems that we're trying to solve as a project, who's funded the project as a whole, and why we're actually doing it. Also highlighting who's involved with this, because there's 9 organisations involved in this project, and how we're aiming to solve this. Obviously, then it'll be followed by the Q&A that I previously mentioned, and a bit of a wrap up afterwards. Next slide, please. Okay, so what is Airspace of the Future? So it's a project, an 18-month project with 9 organisations. The project came together and created a vision statement in which it kind of pulls together everything that we're aiming to achieve within the project. In particular, It was created to capture the objectives of the project. So looking at end user requirements, business cases, the synthetic environment, the stakeholder engagement, whether that's public or targeted, which will then be underpinned by the transport model and a roadmap, just to say where we are now and where we're going to be moving forward. Next slide, please.
So that's a very detailed mission statement, if you like. And at the beginning of the program, we began to understand, or began to think about what that actually meant in terms of deploying drone systems into the airspace. And we came up with this a bit of a thumbnail sketch, if you like, as to the elements that we needed to consider, how they would integrate, and what we needed to do. And looking at the diagram in front of you now, you can see that we're looking at multiple drone operators. So we've got 2 drone control stations. We understand that in a business model, there's going to be more than one UAV traffic management system. That's the UTM systems at the bottom. We need to integrate with manned air traffic management. We need to understand how information moves around the system, whether that's to give us situational awareness as the radar systems there, but also linking back into airspace management to ensure primarily safety of the operational system. So we potentially need a GPS feed to give us not only navigation, but also perhaps to gain access into ADS-B systems to allow us to better position drones, not only to understand where they are, but who they are and what they're doing. So this was our, if you like, starter for 10. We had to start somewhere, and this is what it looked like. So if you move on, please. Next slide. We then began to look at that and begin to capture it a bit more of a scientific way, where we said, okay, we've got rural areas, critical infrastructure, urban areas. We need to integrate with piloted aviation. We've got a large number of systems that we need to ensure operate concisely and together seamlessly and safely. Next slide, please. So where are we in the airspace? We started off with, we know that airspace has lower airspace, middle and upper airspace for manned aviation. And there are various classes through A to G, each with different constraints and rules and regulations that surround them and manage them. For drones, for this program, we wanted to look at the very low level sub 500-foot airspace zone, which as a general rule, and I know there's an awful lot of challenges to this, manned aviation tends not to operate in that low level airspace, noting the fact that obviously every time they take off and land, they have to pass through it. But generally, manned aviation tends not to operate in that area. Obviously, there's probably an awful lot of exceptions to that. So looking at that sub 500-foot level, we've begun to look at what already exists rather than reinventing any wheels. And we've looked at the EASA CORUS CONOPS, EASA being the European Union Aviation Safety Agency, and CORUS being an acronym which stands for Concept of Operations for European UAV Traffic Management Systems. Quite how they get CORUS out of that, I'm not sure, but anyway. And they look at this low-level airspace type, where they break it into different zones of type X, type Y, and 2 types of type Z. And X, Y, and Z have increasing levels of risk associated with them. So if you move on, please. Next slide. So what are the challenges associated with drones and getting them to operate safely in this airspace volume? Well, currently, drones tend to operate within visual line of sight. They want to move on, and one of the keys to drone operations and a business model is being able to move to flying beyond visual line of sight. That is, beyond the ability to, by the Mark 1 eyeball, being able to manage the drone and the airspace around it. Currently, planning missions is very manually intensive. There's a lot of work, a lot of paperwork, a lot of issues that need to be overcome in order to streamline that. And there's no coherent airspace deconfliction for drones. There are pockets of it, but it isn't UK wide, and it certainly isn't managed completely accurately. There's no unified and constrained airspace management systems either. And really, nobody's done a lot of work on understanding business modeling for drones and UTMs. So there's a lot of things that we need to look at from the regulatory, the business, technology levels to enable us to deliver on the statement we started off with. So next slide, please. So looking at the airspace of tomorrow, drones operate. Next slide, please. And in the future, we see increasing levels of drone operation. You know, there'll be a higher capacity. We'll be able to, in order to reap the benefits, we need to do this. And we understand that, but that's only from the drone operating perspective. What we also need to understand, next slide, please, is what's happening with the general infrastructure, the management processes, the ability to manage drones safely, securely, allow equitable rights to the airspace. If you can see on the bottom right there, there's elements of infrastructure that need to be put in place. And on the bottom left, there's systems in order to manage the airspace, whether they're cloud-based, whether they're physical systems. And what needs to happen is these two worlds need to live in harmony so that the drone operators have easy access and can almost operate seamlessly into the airspace using this infrastructure that sits on the ground or in the ether to enable management to take place safely. Next slide, please. And that's what we need to do in order to get us to the point where this future drones volume that I talked about earlier across all airspace types is accessible. Next slide, please. I'll pass back to Courtney.
Thank you very much, Phil. So one of the things I'd like to highlight is this project wouldn't be possible without the funding aspect, as you'd imagine. So this particular project is actually funded by Innovate UK on behalf of UKRI, which have put £125 million towards this challenge, which has been matched by industry funding of about £175 million, which is hugely significant. And it's basically there to enable us to kind of move forward within this kind of area as we progress forward. Looking obviously in particular, looking at the future flight elements that are on the screen. Next slide, please. Perfect. Within this particular slide, what we've tried to do is capture the problem, how we're trying to solve the problem as a whole. So you've got the challenge with the world and the landscapes. So one of the things we're going to do within the project is use cases and business modelling with stakeholder engagement and elements to support that. There's airspace management and the regulatory engagement aspects. But then this is supported by the infrastructure, whether it's regional, national, and the enterprise architecture as a whole, supported, which is helped and enabled with simulation and the digital twin. We have got a small element of demonstration, which we'll come on to describe more. And then obviously, how do we succeed after this project? So the future exploitation elements. Next slide, please. So as we mentioned previously, there are 9 organisations within this project. Can I please introduce Altitude Angel?
Yeah, good morning. I'm Philip Bink from Altitude Angel. Altitude Angel is a technical company developing unmanned traffic systems, set up about 7 years ago by our founder, Richard Parker. He's a really enthusiastic drone operator and he's a technically minded, but he started to realise actually airspace is a little bit more complicated than just to fly a drone. It is more complicated than it first appears. And so he thought he would introduce technology to bring all the appropriate information to enable people to fly drones safely and in the right place. And that was the start of the foundation of our Guardian UTM system. From there now we've grown. The Guardian UTM system is accessible in 152 different countries around the world. We have approximately 50,000 flight plans a month submitted into the system. And we have over 100 million interactions with Guardian UTM. And that's people finding out data about airspace data, ground hazard data. From there now, then we support 4 ANSPs, and we quite simply just have one mission. We want to get drones integrated safely into the airspace. And this is why we've joined. This is why we decided to join Airspace of the Future. It's all about that beyond visual line of sight, enabling drones to access the airspace. But of course, it must be done safely. Over to Ocado.
Great, thank you, Phil. So good morning, I am Duncan Russell from Ocado Technology, and our founding vision was to transform online grocery through cutting edge technology and automation to operate online grocery profitably, scalably and sustainably. Ocado has developed some of the world's most advanced capabilities in the areas of artificial intelligence, machine learning, robotics and digital twins to build the Ocado Smart Platform, which is an end-to-end e-commerce, logistics and fulfillment platform based on software as a service and including the technology to operate automated warehouses. The solution is not limited to grocery. The Airspace of the Future project is an opportunity for us to be part of the evaluation of complexities of operating aircraft in various use cases. In particular, Ocado Technology is looking to understand the inspection of our infrastructure and light payload deliveries. And we look forward to identifying technical requirements for drone services that are robust, safe and secure, and determine the limitations of the operating conditions. Our cutting edge technology powers or will soon power the online operations of 9 of the world's most innovative and forward-thinking grocery retailers around the world. This project is carried out in the UK using the National BVLOS Experimental Corridor Facility. We are happy to be part of the project, evaluating how the drone ecosystem will operate in the UK and across the globe. So it's my pleasure to introduce Thales.
Thank you, Duncan. So it's Phil Vernal again from Thales UK. Thales has approximately 6,500 employees across the UK in 5 different business lines. These include aerospace, space, defence, ground transportation, and digital security. Thales brings expertise in air traffic management systems, complex systems integration, simulation and modelling, and we've also got a nascent UAV traffic management system, which actually has recently been rolled out in the USA. Just to give you an idea of the sort of thing we do, if you've ever travelled by air more than once, odds on that the Thales system has actually been part of your flight management. From this research program, Thales wants to gain understanding into the UTM regulatory pieces, operational business models for drone enterprise, advancements and advance its UTM development program. And also Thales is the prime and the technical lead for this program. So I'll pass over to the Connected Places Catapult.
Phil, thank you very much indeed. And good morning, everyone. My name is Andrew Chadwick with Connected Places Catapult. So Connected Places Catapult, we're the UK's innovation accelerator for cities, transports and for place. And one of our roles is to tackle market barriers and particularly focusing on 3 areas of strategic opportunity, which are levelling up and regional productivity, accelerating the transition to net zero, and also restart and recovery post-pandemic. We in the Connected Places Catapult lead on a number of programs of relevant to the Airspace of the Future program are the Drones Pathfinder and Pathfinder Catalyst programs, and also our work on the Open Access Unmanned Traffic Management Framework program. In the Pathfinder program, we perform real-world demonstrations which bring to life the benefits of drone solutions. We're developing case studies and economic analysis for each of those. And also we're researching and engaging to understand public views of drones and address public acceptance. And we bring all the aspects of those programs and the other work that we do and perform into the Airspace of the Future program. And as I said, taking that further to the next steps. And I'll hand over now to Cranfield Airport. Thank you.
Good morning, everyone. I'm just covering for Alex Williamson, our uncrewed aerial systems accountable manager for Cranfield Global Research Airport, that is a fully licensed air navigation service provider and airport, obviously co-located at Cranfield University. We have installed our first civilian fully digital air traffic controls tower that has been introduced in the UK. Cranfield Airport is providing leadership and direction in collaboration with our partners here for Airspace of the Future to define how airspace should be modernized and to enable especially how beyond visual line of sight operations of uncrewed aerial vehicles can seamlessly and routinely safely be conducted. We are working closely as an airport with the UK Civil Aviation Authority to ensure that airspace design and new airspace design are credible and can be implemented. Alex, being an accountable manager and holding a Civil Aviation Authority operational authorization for both Cranfield University and airport, enables us to conduct operations of uncrewed aerial vehicles that are safely integrated into our existing airspace. And we can, in this way, do controlled testing of operations that wouldn't be able to be done in the real world. This is what we're bringing into airspace of the future. And our experience of regularly flying these kind of systems at the airport, primarily for research purposes, but that informs both the regulator and the project here of airspace of the future. Can now pass on to satellite applications catapult.
Thank you, Dimitry. Good morning to all. My name is Marcel Kintan. I work in the Satellite Applications Catapult. And the Satellite Applications Catapult is one of the network of UK technology and innovation companies which aim to drive the economic growth of the space sector through the commercialization of research. Within this particular context and the drones domain, we focus on one side on supporting the UK industry in the commercialization of drone applications and services, as well as the emerging urban air mobility markets, with the use of satellite and associated systems. And secondly, supporting the ground, air and space infrastructure, implementation and deployment for the safer operations of these iSpace users. Within the context of iSpace of the Future project, and from a technical perspective, our work focuses on wireless connectivity using satellite and cellular communication networks, with an emphasis on the command and control link, the C2 link. In order to achieve this, we perform the characterization and parameterization of this wireless connectivity based on the regulatory framework and standards, and this will help producing a modeling method and tool for planning and assessing the communications infrastructure, for one side, scalability and serviceability, for instance, quality of the service in a specific iSpace volume and density of iSpace users. Our main objective from the study is to compare and improve the fidelity of the method and in simulations and in real scenarios with the flight trials we can undertake. This will provide a better understanding of the communications performance to achieve two things: to recommend new features and requirements for engineering onboard connectivity solutions and products. An example, for instance, would be new novel modems and antennas, or for instance, location of the antennas for a better performance of the connectivity. And second, to recommend the usage and deployment of ground infrastructure for a better connectivity, servicing those iSpace users. Thank you very, very much. Now I hand over to Blue Air.
Morning, everyone. My name is Gavin Gowdy, and I'm the Operations Director at Blue Air. We're based in Bedford, and we've got about 70 or just over 70 employees. Blue Air have been working with autonomy and unmanned systems for over 22 years. We're at the forefront of unmanned systems and autonomy research and development. We've got a proven track record in delivering fast-paced and challenging programs. Our technology is centered around our own SNAP flight management system and our Nexus ground control stations, both of which carry algorithms, control laws, and software that we have developed in-house. Our capabilities include the design, development of entire unmanned systems, including the flight control systems, ground control systems, flight service provision, and advanced modeling and simulation and system certification. We're committed to providing value-adding effective solutions in rapid timescales in support of both military and civil markets within the maritime, air, and land domains. Our activities with the Civil Aviation Authority, including the National Beyond Visual Line of Sight Experimentation Corridor, or NBEC, form a key component of the Airspace of the Future project. Our role in the Airspace of the Future project leverages our system development, modelling simulation toolsets, flight testing capabilities, and our extensive understanding of regulatory aspects to help identify, develop, and test airspace design considerations, including necessary technology and procedural aspects to accommodate by the use of suitable adaptive procedures and ultimately integrate in accordance with fully routine standardized processes for all types of aircraft. I shall now hand over to Cranfield University.
Hello again. So I'm Dimitry, Head of Advanced Air Mobility Research at Cranfield University. Cranfield University is an exclusive postgraduate university, a global leader for education and transformational research in technology and management. We focus on specialist themes like aerospace, defense, security, and have an unrivaled reputation for education, defense research, and consultancy. We cover in research and development the entire aviation ecosystem, so what we call the 4 A's, so aircraft, airspace, airport, airline. And at the core of it, we put passenger experience and service, digitalization, systems integration, and business resilience to encompass those themes. We cover the entire range of technology readiness levels, so from concept development to prototype design, and using our airport capacity that I introduced before, we can do the whole range to controlled operational testing in an airport operational environment. Within our new Digital Aviation Research and Technology Center, we are hosting now the digital twin and synthetic environment that we are building through Airspace of the Future. And we look to push the boundaries on research that enables a seamless and safe integration of all new future autonomous uncrewed aerial vehicles into conventional air traffic. Cranfield Airport has recent experience of successfully implemented an airspace change proposal for a dedicated beyond visual line of sight drone corridor to enable detect and avoid research. And that informs as well Airspace of the Future, and we're using as well the project outcomes of Airspace of the Future to even develop that vision further. And with that, I will pass on to Inmarsat. Thank you.
Thank you very much, Dimitry. Unfortunately, Inmarsat were unable to make today's webinar. So if we go on to the next slide, please.
So, as I've previously mentioned, we've based our program upon the chorus concept of operations. And when we look at this, you can split this down, as it says, into type X, type Y, and type Z. Now, in order to operate in those types of airspace, there is an increasing level of capability from a foundation level at U1 all the way through to a full level at U4. These levels of capability are not only for the platform, but they are for the system. And they impose increasing levels of technology to meet the demands of the increasing risk level moving across those layers from X through Y and into Z. Move forward, please. Next slide. So as we've mentioned earlier, and as Courtney has mentioned, we needed to break the program down into a number of different research areas to enable us to really begin to delve down into solving this problem. And as you can see, those on the left-hand side, I mentioned we've got a development of use cases, understanding public perception. Key is the regulatory and legislation piece, the business modeling and business cases, supporting services which are required to operate this system, the technological solutions needed, and all these have been captured in an enterprise architecture. And we'll talk about all of these things in the up and coming slides. All of these cases will culminate in some trials and demonstrations, which again we'll talk about later on. Now, you may ask why we chose Chorus and why we chose this particular route to go down, this European route. Well, that was because at the time, probably over a year ago, when we were beginning to think about how we wanted to go forward and what we were going to do, the development of requirements and specifications for unmanned platforms and their management systems was fairly well in its infancy. And the people who seemed to have the most advance were the European Union of Aviation and Safety, EASA. And our own UK CAA had actually worked quite closely with the EASA in developing these. So we felt that this, as recognized as being one of the more robust models going forward, we didn't want to start from a clean sheet of paper. So we felt it was better to move forward, standing on the shoulders of giants, as it were, and use this to take us further forward. So obviously the other point of this is that we're not going to jump straight into a U4 capability in this program. We expect probably our technologies to reach somewhere between U2 and U3. But with the use of simulations, we can research into what is needed and how we would operate all the way through to a U4 capability. So that explains why there's a time domain along the bottom. So if you, next slide, please. So we're now going to take a 5-minute break. Courtney, do you want to set a time to reconvene?
Yes, absolutely. Thank you very much, Phil. So we will reconvene at 10:36. I repeat, 10:36. So we'll see you all back here then. Thank you very much.
Thank you.
Brilliant. Thank you, everyone. I hope you all had a great break. So, Phil.
So now we're going to take you through each of the particular cases, and I'm going to introduce Jamie to talk about the use cases.
Hello everyone, I'm Jamie Chan-Pensley. I'm one of the technical leads for the Connected Places Catapult, and I'm going to take you through the first element on how the project is addressing the challenges of the airspace of the future. So considering the overview that Phil just provided, the first activity for us to undertake was to gain an understanding of the prospective traffic and usage of the airspace. So we focused on developing a set of use cases and to capture a set of end user requirements and to actualize these activities and the sort of tasks that may occur. So additionally, a set of business cases were created to understand the financial viability and the potential activity of how busy this future airspace was going to be. So next slide, please. So in developing our use cases and business models, we identified an approach that needed to be thorough, but also sensitive to the work currently performed across industry. We recognize that there's a wealth of existing information and research, and felt it was really prudent to establish a solid baseline of understanding of this airspace, and by performing an extensive literature review and to engage with experts and stakeholders from the field. This was really key in grounding our research in something that was practical, realistic, and applicable for a future time frame of 2030. This was a target timeline that we set as a challenge for our airspace of the future. So after gaining an initial baseline of 129 initial activities and insights, we built a database of key potential activities for drone use. This led to a development of criteria that we used to focus the work, so leading to a set of key clusters that we used to prioritize and provide a foundation of building blocks for the other activities. These would holistically challenge the boundaries of different aspects of the airspace, so scrutinizing elements such as regulatory space, creating a digital twin and simulated activities, the enterprise architecture and physical trials. So these use cases would fundamentally define the focus in terms of the airspace occupancy and therefore regulatory compliance in the traffic management. So our research drove us towards performing a detailed set of business cases and creating an airspace air traffic prediction tool. This would help us to understand the important aspects of how the airspace would be utilized and then the potential traffic within. So next slide, please. So we developed a full set of business cases, and this was in order to firstly prove that there was ultimately demand for these sorts of services. Secondly, that there was a sustainable business model that could be developed from each of these examples, and at the same time to understand the enterprise cost modeling. Thirdly, we wanted to get a first look to gauge the break-even point of the enterprise and the different potential pricing strategies for each of the use cases. And this was because they had a number of differences in their nature. For instance, some might require subsidies due to a high social impact. Others might depend on flight planning notice time, and others might depend more heavily on geography and time of day or access to the airspace. So we focused on the following 3 business cases and spoke to a range of expert end users who've really helped to provide key details and richness that's validated and increased our understanding around their areas of expertise. So the first case focused on inspections. These were examinations of long linear infrastructure, for instance, power lines or railways, and using artificial intelligence to detect critical faults on the inspected object. This was chosen as it helped demonstrate activities along an extensive infrastructure item, and that could be scheduled, unscheduled, and across a range of different environments. Blue light services. So this included police emergency response, and for example, the use of drones for surveillance, tracking perpetrators, search and rescue. This was an interesting one as it was a potential interrupter for the airspace, and the way in which it operates might require an emergency ad hoc operation, or it could be actually part of a coordinated or planned activity. And then the third was light goods transport. And this was around the delivery of consumer goods to a customer with a payload under 3 kilos. This had a potential for high volumes of activity and coordination required throughout the system and across different environments. This had significant potential to impact the airspace as we know it. Can I introduce now Duncan Russell from Ocado, who will provide a bit more detail around this light goods transport business case. Duncan.
Hi, thank you, Jamie. So the light goods delivery use case has been developed with a subset of the general deliveries in mind. And we defined light goods as less than 3 kilograms that would augment and extend existing deliveries that currently operate via roads using vans, motorbikes, e-bikes and manual push bikes. We are investigating how these drones would complement these current models of delivery and look at the potential to reduce overall costs. In particular, the drones can support deliveries in a short time scale and help to respond to dynamic demands. The short delivery time is achieved by avoiding congestion on roads, and itself removes the congestion and some traffic from the roads. We can see that the other potential to reduce impacts on the environment, since the drones are based on electric propulsion. And the use case itself does not include the delivery of the full grocery order, but does ask the question about how the drone capabilities and what the ecosystem and airspace management would look like to support the drone delivery light goods as part of an overall delivery service mix. That includes looking at other solutions across the world, how they're trialing deliveries, and what kind of locations they're able to deliver to at the moment. So I'll hand back to Jamie for the other use cases.
Thank you, Duncan. So next slide, please. So our research also enabled the formation of a set of high-level outline strategic business cases, and these were aligned to the project scope. These were examples with a high expected industry saving, expected to be in operation in 2030, and exclude the visual line of sight and operations in open airspace. So these use cases were taken in consideration and of specifically how they'd integrate with the overall airspace. And for the strategic business outline business cases, further understanding was required of aspects such as operational, economic, environmental, and social impacts that they might have. So from an operational perspective, we wanted to review elements such as understanding what would be needed to make the use case function, from potential infrastructure and functionality requirements, just to make this possible in the 2030 timeframe. The economic impact reviewed elements such as the profitability, the scalability and the costs. So understanding the market opportunity and application across multiple activities. The environmental impact, so consideration of visual, oral, and ecological impact, and that around the potential airspace traffic of the future, how that's going to integrate with the ground services too. And then social impact, understanding public acceptance, the interactions of people with each of these use cases. Was there a societal benefit? And this might not have been considered with a lot of other models which are more focused on commercial or economic measures. So these were combined with a market analysis to really help understand what was the scale of this opportunity, what were the adjacent markets. Combining this with understanding associated costs around the UTM and access to the airspace, this enabled us to analyze potential models, financial viability around these use cases. This helps ultimately construct the value proposition, and this will identify whether or not there is a need being solved, the traffic implications, and the impact on the airspace. Next slide, please. So by compiling the work generated from across the project, we've gained a really comprehensive understanding of different factors for the future airspace. We've now been able to develop a view of how the airspace will be used through a wide set of use cases, who will be using the airspace through the involved stakeholder engagement and analyses, an idea of the volume of traffic through a bespoke tool created by the project, and the likely costs and the value proposition through the business model work. With all these in mind, it identified a range of challenges around the airspace, and that's led to our engagement around regulations. So can I now introduce you to Phil Binks from Altitude Angel, who'll take you through this part of the programme. Thank you.
There we go. Technology is not a strong point. That's why I've got a great team behind me, Altitude Angel, to help me out with technology. So first of all, for those who don't know, who are the regulators then? And the regulators are Civil Aviation Authority here in the UK. And they deal with all aspects of civilian aviation. So the main aim, obviously, their key aim is to protect all airspace users. And also thinking about the people on the ground, of course. If there's an incident in the air, it may have a direct effect to the people on the ground. So they're trying to keep everybody safe. So as part of this project, integrating drones safely into the airspace, the engagement with the CAA is absolutely fundamental. And I think that's probably answers some of the questions, or one of the questions that came up in the chat, that why isn't the CAA involved? And they absolutely are. So how are we engaging with the CAA? Well, the Future Flight Challenge team, establishing a number of projects for the Future Flight, realised there's going to be a big impact on the CAA. There's going to be a big demand for the CAA's time. So what they've done is each project was nominated a point of contact within the innovation team. From that point of contact, as that person starts to learn about the project, they will start to identify and engage with the SMEs within the CAA themselves. And so we get a nice coordinated approach through the CAA and get the right engagement with the right people in the CAA at the right time, which is really, really important. We certainly can't afford to waste the CAA's time. They're far too busy for that. So as we've already sort of discussed, how did we start? Where did we move forward? Where did we start from, and how did we move forward? We are focusing on beyond visual line of sight activities. And of course, as previously mentioned, we started off on the chorus model, the ARSA chorus model. This is a concept of operations about how we go to integrate drones into very low-level airspace. And as mentioned, why did we use the chorus model? Well, the CAA was heavily involved in development of chorus. And although the UK hasn't officially adopted chorus, it was a great place to start. The CAA are familiar with this, and therefore we could start moving forward from that position. There are these new classifications of airspace, then X, Y, and Z airspace. And Z is broken into two elements, ZA and ZU. One is for airports, airspace around airports, and the other is ZU is an urban environment. Each of new classification of airspace has a number of services attached to it. For example, X airspace is effectively aligned to Class G airspace today. There's no direct control or management of aircraft in that airspace. And all we need, the services required for that airspace, is a registration, electronic identification. And that's basically it. There may be some geo-awareness information also. As we move to Y airspace, we're starting to move into more complex airspace, and there's greater risk of operating in there. It could be over a sort of critical national infrastructure or something along those lines. And therefore, we start to introduce more services in association with that in order to make sure there's an element of managed traffic in that area. And then finally, when we get to Z airspace, whether it's ZA or ZU, this is now coming into a very dynamic piece of airspace. It's starting to become very, very complex. It could effectively be very dense, over densely populated areas and a lot of traffic operating in the area, a city, for example. So again, you have more and more services being applied to that airspace to ensure that the airspace remains safe. Obviously, this wasn't all done in one go. Chorus set up use space 1 to 4. Use space 1, I've already mentioned, is the foundation services. And these were registration, identification, geo-awareness. Then the next phase was the initial services, aeronautical information, tracking and monitoring capabilities. And finally, we move on to more of the advanced services, like dynamic capacity management. And then we start to have this far greater interface with ATC. So for this project, what we decided to do, with all that background going on there, we wanted to look at and review the existing management frameworks we have and identify the gaps, that are around, which will be required, if we can get this sentence out, to support future airspace management. And we start looking at do a little bit of a gap analysis, and we start writing up a paper on that. The whole purpose of this is to inform the CAA, help inform the CAA, and help inform and help the UK move forward, their drone industry forward. We also looked at aeronautical communication and data sets. So the data sets are quite an interesting one. For manned aviation, there's a recognized number of data sets. We look at NOTAMs, for example. We have AIS, Aeronautical Information Services, currently managed by NATS. And it's quite a recognized amount of data, or what data is required for manned aviation. Unmanned aviation is very different. We're starting to look at a lot more airspace hazards, and also ground hazards then start to come into play when we start to think about flight planning. Ground hazard could be restricted airspace over something like a prison, critical national infrastructure, railways and things like that. So all of this data, this new data set has got to come in. So we start needing to look into what additional services and infrastructure is required. Apologies about that. And see what of these are going to be, how this is going to be fed into, and how it helps manage the airspace of the future. And finally, we're looking at sort of identifying or proposing the data formats and data requirements and data exchange requirements. We're starting to look at data sets that have never been considered before for airspace or for aviation. So where do we get that data from? Is it coming from an authoritative source? How reliable is that data? And we start to look at all of these bits and pieces. We're also having to look at more sophisticated weather information as well. What about hyper-localized weather? That needs to come into play when in certain elements. If you start to operate in a city and you get urban canyoning, are we going to get funnels of wind going down particular roads or routes throughout that city, depending on where the prevailing wind is coming from? So all of these data sets must be thought about. And obviously there's another key one, is all the ground hazards that's coming into play there. So there's lots and lots of additional data sets that are coming in, and we need to make sure that all of this information is integrated correctly, so the airspace can be managed properly. So this project is looking at these kind of elements. And so then we can start to have these discussions with the CAA. Now, the good thing about having this continued conversation with the CAA throughout the whole project is, as you can imagine, as you start scratching the surface from these, scratching the surface of this project and start digging into the weeds layer by layer, it starts to get more and more complicated of what we're actually trying to achieve. And so engaging with the CAA, they just make sure we don't run down a rabbit warren, and they can start pulling us back and say, guys, you perhaps don't want to look down here. Perhaps you need to think about the project going off in this direction. So we're not wasting time. That engagement is absolutely critical, and it helps move the project forward in a timely basis. But of course, now we're starting to build a system of systems, all this activity that's going on. Cybersecurity then comes into is a big question, and also privacy. So how can we make sure that the appropriate cybersecurity or the appropriate security mechanisms are in place? And again, it's another big question that we're also looking at. And then privacy. More than ever before, people are concerned about their privacy, the amount of data that's flowing around. And privacy is absolutely key to ensuring public acceptance. If we don't get public acceptance, drones will not be accepted, or drones will not be adopted widely across many industries. So these things are absolutely critical to make sure we move the industry forward. We are working on those. We are liaising with the Civil Aviation Authority, and we're looking at how we can address any concerns and issues. So on that note, can I forward you to Thales, I believe, and to discuss the enterprise architecture?
Thanks, Phil. Good morning, good afternoon, good evening, wherever you are in the world. I hope you are well. I'm Joseph Lamb, a Principal Solutions Architect from Thales, and in the next part of this webinar, I'll guide you briefly into the development aspects of what we're doing. So the first pillar is the enterprise architecture, which essentially is capturing design and is the blueprint to describe the various dimensions of this project and the space that we're investigating. One of our colleagues and partners will talk about the digital twin, which essentially combines the synthetic environment and data with real systems. and a little bit about the real future world in terms of the trials and demonstrations. Next slide, please. So looking at this diagram here, you see the big red box, and essentially the enterprise architecture blueprints will capture a number of views and perspectives from these sort of key enablers that you see from use cases that Jamie described earlier, and sort of the regulation bits all the way to sort of the technology and solutions aspect. And it's quite important for us to understand it in terms of an architecture, because it captures and structures sort of the logical entities, understands their sort of relationships and complexities around that space. And it's important for us to do that, so that towards the end of our project, we're able to describe that and share it with industry. Next slide, please. So let me give you a bit of a definition of what an enterprise architecture is. And I appreciate that not everyone is familiar with this, so it's worth covering sort of the basics. So what is an enterprise? So simply put it, an organization or organizations that share common goals and information. So that's sort of the enterprise sort of definition. Formally, in terms of architecture, there is a standard for architecture definition, and the one we're using here is ISO 42010. And that says fundamental concepts or properties of an entity of interest in its environment, embodied in its elements, relationships, and in principle of its design and evolution. So coupling those together, enterprise architecture actually encompasses strategy, business, and technology. A good analogy that to help you understand it, if we look at the bottom diagram here that we see of Heathrow Terminal 2, that graphically or pictorially looks quite aesthetically pleasing. Architecture isn't just about aesthetics. Good architecture considers sort of structures, organizations, cohesive functional and non-functional properties, people, process, and technology. So from a perspective of someone going to an airport, the experience of arriving by public transport, walking off into the terminal, checking in, going through security, all the way to either to a business lounge or having some refreshments, and then eventually being greeted and boarded onto an aircraft is one aspect of it. But then we have to consider from the facility side of the airport, we have the bathroom facilities, shops, the lighting, the heating, the air conditioning, and then from sort of the aircraft rolling up to the actual terminal itself and the baggage handling. You can imagine all those things come together to make the functional properties of what makes that a really good architecture. And also, as you probably experienced, there are some non so great properties about your experiences going to an airport from different dimensions. But regardless of that, the sum of the parts equates to what contributes to making it a good architecture. And on this program, what we're trying to do is understand the sort of the holistic understanding of what we're trying to achieve about the future airspace. So next slide, please. So giving you a little bit of an overview of how we've broken down the layers, and this is a very simple depiction of the actual concept model and of the blueprint that we're doing. At the very top, we have the enterprise layer, which as described from one of our partners already, that we talked about business models and identified use cases. Essentially, the question we're asking ourselves here is how to practically operate the management of airspace as a business. And that's kind of what the enterprise layer is trying to look at. The next level down sort of describes the logical entities, the context of the airspace and entities, rules and regulations, the processes, the activities, procedures, and also not forgetting the airspace users and stakeholders. Essentially, this layer is asking what are the key rules, processes, and capabilities required. And towards the bottom of the layer is essentially the technical solution. So these areas identify what current technologies there are, the analysis of where the gaps are, and potentially propose technology roadmaps of where the technology isn't either there yet or needs to evolve to sort of address sort of the logical space that we described in the middle. Essentially, it considers what actual solution combinations can achieve this. And we're not saying that one technology solves all. There is it is an ecosystem, so we need to consider there's current technology today and the evolution, what it will be tomorrow. So yeah, that's a little bit of a nutshell of what the three layers are. So and then we've also got the time domain, which you see in the green box. So all these layers have to consider that aspect of today's today's picture moving forward to the future. And it will be an iterative step, and we can't forecast everything, as far as 50 to 100 years. But what we try to do is understand the evolutions that need to happen as part of those layers, and that will help industry move forward to how to work together to understand this sort of airspace. So next slide, please. So just giving you an example here of some views that come out of the model. So we're using a modeling approach to realize sort of the architecture. On the top level that you see in white are the sort of high level views. So this is for the partners and ourselves just trying to break into the sort of model and understand sort of the presentation aspects, sort of the requirements and sort of references, glossaries and common terminology and taxonomy around the architecture. The next level down is the enterprise view, so things like the higher geographical sort of views of where things are, the business and financial modeling, and sort of the capability type roadmaps. And then the big bulk of it, which I'll talk to you later in the webinar, is around sort of the use cases. So things that were described by Jamie about the use cases, we've taken one of them and broken them all into its constituent parts to depict what each layer is, and trying to unpick sort of the complexity around understanding, so sort of that logical area. And we haven't forgotten the regulatory views in there. They play a huge part in how we shape and understand these sort of areas. And at the bottom there, you can see there's some physical views, and that's capturing a one instantiation or one combination of current technology and how it could solve sort of that operational, the logical space. And we've started to understand how we represent that as a initial trials and sort of demonstration system views. So that just gives you a flavor of how some of the views are being represented in the model. And there's obviously more connectivity, but just to keep things simple, that's a simple depiction of how the views are being represented. Next slide, please. So I'm going to give you a brief overview of some bits as an architectural product. On the left-hand side, breaking things down. So we on the logical layer, we've got the context, and that describes sort of the introduction to the use cases. As you heard from Ocado earlier, if we took a light goods transport sort of aspect, that gives you the context of what light goods transport is, what things are being addressed, how we plan to use, or the users plan to use that, and how we intend to manage that airspace, what type of rules and regulations. So it gives you the high level overview. That's what the context is for. Then connected next level down is sort of the logical entities interactions. I'll talk about the diagram on the right, so I'll just get through the bits on the left, and that describes sort of the logical entities that are involved in this space, what interactions they have. And then on those interactions, the next level down is the information exchanges. And that's basically on those interactions, what are the key information at the highest level needs to be passed between these entities. And then the next level down is sort of the activities and processes. And that basically shows how that information is generated. So essentially what activities generate that information exchange or passes of data across the entities. And then at the sort of next level down is sort of the solution type views, which basically transfers us out of the logical groupings into the real world, and what technology will address that type of capability. So on the right-hand side, as you see here, and as mentioned, this is a product of the architecture. And this is a very simplified view, just to make it easier for you to understand. So there are essentially 4 key boxes on that screen. You have the use case scenarios, which embodies what the context of where we are planning to operate the drones and sort of the traffic management side of things. And then on the box on the left is essentially core enabling and third-party services. These are, examples of these services can think from weather information, aeronautical information, geographical sort of terrain information, rules and regulations, things that enable sort of the center bit, which is the UTM and the drone operations type box. And as you can see there are quite logical entities that you may recognize. There are drones, there are drone service providers. The core is a sort of UTM or drone traffic management service provider. And on the sort of the bottom bit of that that box, you've got the other airspace users as expected, which are piloted, which aren't drones, and also airspace traffic managers, your classic ANSP sort of piloted aviation managers there. And then on the right-hand side are sort of interactions with the specific use cases that were here. So for example, if we talk about light goods transport, there'll be the stakeholders and the customers for the as in the end customers for the grocery shopping, for example, on that aspect. And maybe you have to consider their infrastructure. You know, are we going to a housing estate? Are we going to someone in a field or someone in the beach? And that kind of covers sort of the terrain and topology aspect. So we have to consider the interactions across those three bubbles there. So I've described sort of the 4 boxes, and as you can see on the red lines on the screen, or the lines essentially with little bubbles on it, essentially those are the interactions, and we're saying that there are logical interactions between those entities there. And what I'll talk to you in the sort of next slide is what actually lives on those actual interactions, which is the information exchanges. So could we go to the next slide, please? Okay. So as you saw in the center column earlier with the UTM and sort of drone operations, I've taken out some of the entities there. So we've literally gone down to drone service provider and UTM service provider, and an interaction between N+1. So we assume that there's not just going to be a one service provider model for traffic management. We consider that it's going to be an ecosystem of different partners. As you can see with the blue circle there and the box on the right, that if in the model, this is what you'll in our model, as we see, we click on it and it actually gives you a more richer picture around what is the information that lives on that interaction. And just to walk you through, so it shows the directionality. So we've got the drone to the UTM service provider, and there's 4 information exchanges there, from direct remote identification all the way down to sort of alerts and warnings for tactical conflict resolution. So this is more to do with avoiding sort of airspace type collisions in space and ensuring the safety of other aircraft. And then in the other direction, coming back from the UTM service provider to the drones, is again a conflict resolution to inform the drones that they need to deconflict a potential risk in flight. This isn't completely exhaustive, but it just gives you an idea of the flavor of what this model is trying to capture. And we only touched two very small thin viewpoints, and our partners and colleagues will talk about the digital twin and the trials aspects, which again will be captured in the architecture. But for today, I think this is probably a simple enough explanation of some of the bits that we are doing under this. Next slide, please. So having heard about the interactions, those interactions and information exchanges need to be realized in the real world. And I'm going to hand over to Dimitry from Cranfield University, who will talk about the sort of communication network analysis that they've been doing to support us in this architecture development. Dimitry.
Thanks, Joe.
Thank you.
So underpinning this information exchange that Joe and architecture that Joe presented, basically, we're providing the capability of really modeling and integrating as well the end-to-end communication architecture of the future of airspace. So basically, how we model existing communication infrastructure and future communication infrastructure and capabilities as we are looking to scale and develop that future of airspace. So we have existing infrastructure like 4G, comms LTE, and modeling new infrastructure like 5G, comms LTE using satellites as well to be able to seamlessly cover wide ranges of regions, but also seamlessly cover a number of different applications of drone operations. So for example, from urban areas, especially when we have buildings, shadowing, and such effects. So we can model through our simulator and also emulator air-to-air communications, air-to-ground communications, the different performances. We can capture exactly the different scenarios and how that affect on characteristics like path losses and throughput, delay and latency, which would be critical for the for scalability when we cover a number of multitude drones in urban areas especially. So we can model a diversity of applications and diversity of different contexts and techniques, to really optimize that performance, like how we do mobility management, handover management from the different communication infrastructure, some that would be conventional and old, others that would be newer. So again, the crux of it being seamlessly and safely handing over from the different capabilities. As we know, we have quite a lot of existing communication infrastructure, and the idea is how we can leverage that and also optimize it for the future of airspace capabilities. Of course, we do consider everything that would be security and privacy as well, and the different infrastructure that is, for example, heterogeneous or homogeneous kind of infrastructure, servers based, and so on. A bit of a flavor of the different capabilities that we can model and integrate, and how these then inform our end-to-end digital twin and synthetic environment to be able to bring all of the seamless capabilities together to unlock the full potential of drone applications in the future. And to talk to you a bit more about the digital twin, I'll hand over now with the next slide as well to Guillaume from Thales. Thank you.
Thank you, Dimitry. Good morning, everyone. Next slide, please. My name is Guillaume Kerouat. I'm a technical architect from Thales, and I'm going to talk about the digital twin that we are developing with the partners on this project. So next slide, please. And first, I'll start with a definition. So why are we talking about a digital twin and not just simulation or a synthetic environment? So for this project, we are creating an accurate and up-to-date digital representation of an environment, its airspace, and the systems that are operating in this environment and airspace. We achieve that by connecting a synthetic environment and the simulation elements in that environment to real systems and real-time data feeds. And this is this connection to the real world that makes it a digital twin that we're developing as a tool to help us understand some of these challenges. So what systems are we integrating? On the right-hand side, there's a top-level illustration of the different elements and layers that we are integrating in the system. So it doesn't represent the way we're technically putting the digital twin together, but it gives you a good idea of the different elements that we are considering and integrating in the digital twin. So starting from the bottom to have a true representative view of the environment, we start with the terrain layer, which will include elevation data and imagery data. And we can build on top of this layer and add complexity to the environment by adding features, so including natural features such as trees, but also infrastructure elements, so such as buildings and obstacles that Phil mentioned earlier, so power lines, communication masts, for instance, which are very important when we talk about drones, as drones tend to fly quite low in the airspace. The other element that we integrate in the digital twin is the layer just above this, so the weather element. And again, this has a significant impact on operations for drones. Drones are particularly small, so they are affected by weather effects significantly. So we have the weather element in the digital twin. The layer above would include the airspace elements. So this is where the drones and the aircraft, and manned aircraft, will operate together. This is where we apply the new airspace types X, Y, and Z that Phil mentioned earlier. And this layer will also include the systems that help us manage the airspace, so namely the UTM systems and unmanned traffic management systems, which are key enablers and key elements to the overall ecosystem. If we move 2 layers up, I'll keep the comms for the last. 2 layers up, we have our drones. So this is where unmanned traffic is represented, being either virtual or real. And it is mixed with the existing manned traffic, manned aviation, so being airliners, general aviation, or helicopters. And the comms layer, which I've kept for the end, it really is that's relating to what Joe and Dimitry just talked about. This represents the data exchanges between all the different nodes and different systems in the ecosystem that we're representing. So really that is the glue that connects all the systems together. And this is a key element to the study. Next slide, please. So on this slide, I'm just going to give a bit more detail on the different elements that we're integrating in the digital twin. I'm not going to go through all the different boxes, but just to give you an idea of the different building blocks and components that we are integrating in the digital twin. So if we consider the synthetic environment side at the top, where you'll recognize most of the layers that I just mentioned with infrastructure, airspace, weather, comms, terrain. These are the core simulation elements, but also computer-generated entities that provide us the virtual traffic for drones and aviation. On the simulation side, we also obviously have a lot of additional tools, infrastructure elements for the digital twin, and lots of tools that allow us to manage, configure, and control the digital twin as we're running the trials. I'd like to spend a bit more time on the bottom side of this slide, where we show some of the elements and components that we're connecting to in the real world. So I'll just take a few examples. In terms of real-time data feeds, we are using real-time weather data, which provide us with an accurate weather situation awareness that we're able to push into the simulation environment to give us a true representation of the current weather. And the other example is the ADSB, so the Automatic Dependent Surveillance Broadcast System, which gives us an up-to-date and real-time situational awareness picture of the traffic in the area we are operating in. Two real systems that we are integrating with, which are of importance, are the UTM platform. So we are integrating the digital twin to real platforms. It really is for us to be able to test the interactions between the environments, the systems, and those platforms. And the last box I'll talk about is the drone. So we will use real drones, a real drone during some of the trials towards a later stage of this project. So for us, it was critical to be able to connect a drone to the digital twin, from the real world. Next slide, please. So what are we building? I'm gonna describe the area that we've selected to build our digital twin. So the digital twin we're building is represented by this yellow box on this map, and the green area is the NBEC, National BVLOS Experimentation Corridor, BVLOS being beyond line of sight, visual line of sight, sorry. And this is where the NBEC is the area where we'll be able to fly the drones for the trials, the real drone for the trials. So Gavin from Bluebell will provide some more information later on in this presentation, but in a nutshell, this is a physical airspace volume that has been defined where we can operate drones safely with an operational safety case. And for us, it was a critical requirement to have the NBEC within the digital twin because it allows us to mix virtual and real flights during the trials. So we'll be able to fly a real drone in the NBEC while running other operations around it outside the NBEC, but within the digital twin. And just a quick comment on this slide, additional comments at the center, pretty much at the center, we have Cranfield Airport here and Dartech. And we are currently hosting the digital twin elements on the Hilda computer. So it's a high performance computing facility at Dartech. So this is where we're running the software elements of the digital twin. So really we are concentrating on this area of the geographical area. And next slide, please. So I'm going to relate to what Phil Binks from Altitude Angel was talking about earlier. This slide shows how we are mapping the new airspace types X, Y, Z, and Z to the digital twin. And for us, it was important to have a mix of all different types. So we have a ZA for around Cranfield Airport at the center, and then 2 ZU, so for urban areas, in Milton Keynes on the left and Bedford, and also some Y airspaces around infrastructure. So on this slide, I'm just showing there's a power line going through the area. And for us, it was the digital twin that we selected, or the array that we selected, was one of the criteria was to have all the different features available so we can test lots of different scenarios and assumptions and operations, which I'm going to show in the next 2 slides. So next slide, please. So this, again, so mapping between the mapping to the airspace definition, but also to the inputs from Jamie earlier. These are examples of how we can use the digital twin to map to the use cases and test the different use cases. So I've just taken the example of inspection use case. And in this example, you can see a drone being operated to perform some inspection of a solar park and wind farm and taking off from the back of a van. So that will be operating exclusively in the airspace type X, which is the simplest operation. And the second example is the linear inspection of the power line, where the drone will be operating in a wide airspace. So you can see that we can test the different systems to the different levels and test the different services and the different operations and concepts of operation processes that we have to go through to make those flights possible in the airspace. And to highlight this, the next slide will show the same operations. Sorry, next slide, please. So the same inspection operations, but taking off from Cranfield Airport. So the end result is the same. The inspections are performed the same at the end from the mission point of view. But in terms of operations, the use case is very different because we are taking off and leaving and re-entering a ZA airspace. So this has implications on the UTM, the operations, and all the different elements that need to be enabled for, and services that need to be enabled for this operation to happen in a safe manner. So, and finally, I think if we could move to the next slide, this is just to show a few examples, a few screenshots of the different, some of the elements that we're putting together in the digital twin. So on the left-hand side, we have 3D visualization of the Cranfield Airport. So we're using ordnance survey data for this, so including elevation and imagery. And you can see, you can work out the infrastructure, so buildings that I mentioned earlier. And the bottom picture shows the a drone operating around the power line to support some of the linear inspection use cases that we are developing. And on the right-hand side, just a view of one of the tools that we're using to generate the virtual missions around the digital twin. So you can see 3 missions and areas being defined on this interface that will interface with the UTM and generate the drones that will fly virtually in the environment. And now I'll pass on back to Phil from Thales.
Thank you, Gavin. Next slide, please. So we're now going to give you a little bit of an overview on where we're going with the trials and demonstrations, which you could say are the culmination of what we're doing here. So if you move on to the next slide, please. We've talked about the architecture, the digital twin, and live flying. And so what happens in terms of the real world flight trials? Well, this is a bit like the Russian dolls. I know the project team is bored with me talking about Russian dolls, actually, because I do it a lot. But we develop an architecture, and the digital twin can only capture what's been architected. And the live flights can only fly within the boundaries of what the digital twin and the architecture has. So they need to fit within one another. And indeed, the trials we put together can only go to the boundaries of the work that's been constructed. So the real world flight trials actually are an integration of the digital twin piece and the live flight paths in terms of a live virtual constructive process. So if you move on to the next slide, please. On the right, you begin to see a picture of these pieces that are being linked together. The blue box in the center is a simplified view of what the digital twin is going to generate. So it has simulated drones, simulated drone ground control stations, a terrain model, simulated sensors, simulated communication systems so that we're modeling those accurately, and a simulation engine that's running all this. But sitting around the outside, we have real UAV traffic management service provider systems, a real Cranfield air traffic management system, real drones and drone GCS being operated by Blue Bear. We have a set of enabling services, if you remember from Joe's architecture slide earlier, and external sensors. So this really is linking live elements with virtual elements. So what do we hope to gain out of these trials? Well, we need to make sure that the functionality meets what's required, so that the trial functionality offered by the solution elements actually works. So the UTM service providers, all the linkages, etc., all actually enable us to produce the missions that are required. We need to test the operational processes and procedures. So there's the functionality side and there's the process side. So have we got all our ducks in a row to make sure that if we want to do flight clearance, everybody understands what's going on and we have a system that works. And what we're doing is the test cases do come from Jamie's use cases that he's developed to make sure that we are actually testing drone operations that are likely to happen rather than just testing something that's potentially not a real use case. And the overarching piece for this is actually to develop and to give the regulator sight of what we're doing. That's key, so that the regulator can gain an understanding of how we're going forward, because this really is the proof of the pudding is in the eating here, and they can come along and take part in the meal, so to speak. So when are these trials going to take place? We're planning on spring next year. Where? We've already mentioned the live flight elements taking part in the NBEC test volume that runs northeast from Cranfield Airport. This part of the program is in plan currently. So there's not a lot more detail I can give you about the exact test by test case we're going to do. But hopefully that gives you an overview and the general process of what we're doing, why we're doing, and what we hope to get out of it. So I'm now going to pass on to Gavin at Blue Bear, who's going to give you a quick brief on the NBEC corridor itself. So over to you, Gavin.
Thank you, Phil. Yeah, there's been a few of the colleagues today have been talking about the National Beyond Visual Line of Sight Experimentation Corridor, the NBEC. And we've mentioned in the piece that I gave at the beginning that it's quite an integral part of what we're doing in Airspace of the Future, but it's not been developed through Airspace of the Future. It's already ongoing in different projects. And essentially, we look at it, the idea was proposed by Blue Bear several years ago about linking our test facility, which is over to the northwest of Bedford at a place called Twinwoods, to the Cranfield ATZ. And there's this sort of natural 16-kilometre, approximately 6-kilometre long corridor between the two sites, broadly in line with the instrument landing system of Cranfield. So we've created this corridor, and at this current time, we've got a temporary danger area in that space, which is allowing us to do continual beyond visual line of sight operations, and we're doing that quite heavily over the last few weeks, and particularly this week. And by mixing amount of unmanned traffic management services, for example, from Cranfield Airfield, where we've got a digital tower, we've got a synthetic environment, we've got the Availant Gamekeeper, which is a holographic radar system, mixing in some other sensing technologies, using alternative methods of positioning, for example, a Vodafone system, which is called a remote positioning system. We can begin to get a fairly rich picture of what's around, so where we are with the drones that we're operating, and what other aircraft are in the sky. And we're doing this across, a relatively busy airfield environment across fairly sparsely populated land, but also close to other built up areas, road and rail networks, etc. So we've got the full gamut of what's going on really in the overall airspace world. Graham's obviously pointed out in his piece about a general synthetic environment area, and the NBEC is sort of slap bang in the middle of that. So we are doing work now. We're going to be doing a significant amount of testing in the new year, and we're planning on what we're doing there. And it won't just be limited to the NBEC, but it'll have a fairly key role in that. And just some examples of the equipment and infrastructure we've got at the bottom. On the bottom left, we can see the digital tower at Cranfield. The next picture is the Avalent radar when it was assembled at the end of last year. And we're now using that. We've got a couple of our Cobra unmanned air vehicle systems, which we're using extensively on the current testing. Blue Bear's mobile command and control station, which is used for some of the testing we're doing. And the last picture on the right just gives you an idea of how that corridor joins the Cranfield ATZ to Twinwoods, the Twinwoods flying centre where we operate from, where Blue Bear operate from, and how that forms some of the environment that we're going to be operating in. Back to you, Phil.
Thank you, Gavin. Courtney, do you want to take this slide or shall I?
If you'd like to do it, that'd be great.
So we've pulled a slide together with some takeaway messages from today. Capacity, safety, security, and commercial aspects are the key tenets of where we're trying to get to and what we're trying to do. So under the capacity, as the slide says, we need to understand what the future is going to look like in terms of what do we expect the volume of drone operations to be in the 2030 and beyond timescale, because we need to make sure that the current unscalable solutions are scalable. So we need to make sure that air traffic management, drone traffic management are ready to meet drone operations when they become more common. And certainly, as we've mentioned, I think several times, the key is to move from the visual line of sight to beyond visual line of sight capability, which kind of moves us on to this safety piece, in that making sure that that can happen safely, making sure that operations will remain safe is absolutely fundamental. And whenever we talk to the CAA, the first 3 or 4 words they normally will say to us, and apologies to CAA present, will be safety, 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 and safety. Absolutely, and for very good reasons. We want to make sure that what we operate is safe. And security exists at all sorts of different levels. We need to understand the security associated with the drone and the drone operations. And we also need to understand the security associated with the general public. Nobody wants drones taking videos flying over your back garden when you're sunbathing or whatever you do. So there's all sorts of issues associated with privacy. And as I said, data protection. So there's data protection in terms of the product from the drone, but there's also data protection to ensure that the systems are managed safely and there's no cyber piratage or risks associated with that. And the commercial block is kind of important because, unfortunately, well, fortunately, depending on how you look at it, most of the organizations that are going to instantiate systems are commercial organizations. So therefore, for them, it only works if there is a financially viable product and a financially viable process that can be followed. So understanding the price of access to the airspace is key. It's very difficult to do, but it needs to be done, because right now we don't know whether every drone flight, the access to the airspace is going to cost 25 pence or 25 pounds. And we need to understand that, because that's absolutely fundamental to moving the program forward. So all of those aspects we're beginning to consider through this program. We may not get to the end of all of them, but we're certainly considering them all of them and laying the foundations for future studies to take this further forward. So I want to move on to the next slide. Next slide, please. So just to round off with the vision statement, hopefully we've given you today a bit of an insight as to how we're going about trying to solve and to answer this vision state and how to deliver it indeed. I'll just hold that there for a minute. Courtney, do we move on to questions next?
We do indeed.
So do you want to be the MC for the questions section?
I was going to say, I have received a few questions directly with regards to from the participating members, and then we've had a few popped into the Q&A section. So I'm going to start with the first one that's been sent to me directly, and the question is, what is the path loss formula for drone to ground communication? And I think our colleagues at SATAPS are going to be answering that one.
Yeah, thank you, Courtney, for that question. It's actually a very relevant question from a communication perspective. Hi, I'm Dr. Arun Prakash from Satellite Applications Catapult. And regarding the path loss models for UAVs, actually there are several classical path loss models which are very well developed from a standardization perspective for cellular communications, especially for 4G and 5G evaluations. But the issue is that most of these models are tuned for ground-based users, or the terrestrial users. So from a cellular communication perspective, the UAVs or drones, they can be treated as mobile aerial users. So when we consider the path loss models for UAVs, this height aspect has to be considered, or the well-developed path loss models for cellular communications like Okumura, Hydra model, and various extensions for that can be extended to UAVs once the UAVs are below a particular height, especially below the rooftop heights of the buildings. So once the UAVs flies beyond that particular height, the shadowing effects are not there because mostly we have a line of sight condition. So the answer to the path loss model is that the path loss model is a height dependent path loss model. We will have a height dependent parameter along with the standardized path loss models for different, because already there are well developed models for urban, rural, micro and macro scenarios. So if you want to increase the accuracy of the path loss models, we have to do the actual trials, which we are doing in this project, and will be considered in the next phase, where we take the measurements to calibrate the path loss models to add a parameter which is dependent on the height of the UAVs, because mostly the path loss model depends on the distance between UAVs and the transmitter and the receiver. But from a UAV perspective, there will be a height dependent factor. So along with the actual path loss models, standardized path loss models. Thank you.
Perfect. Thank you very, very much for that. And the other one that I've had sent directly to me is, in 2030, what communication capabilities do you think are required to enable successful increase in drone use?
Thank you, Courtney. I think I can answer that. Yes, I would say there are different aspects to take into consideration for from the connectivity perspective to enable successful increase and safe use of drones. We could say technical, we could say commercial, we could say regulatory, and we could say operational. So all these have to be tackled. Let's say from a technical standpoint, and for simplicity, we could divide the problem into the onboard communication system capabilities, and also then on the space and ground communication supporting infrastructure capabilities. What is clear is, for increasing safety and interoperability of and enabling beyond visual line of sight and beyond radio line of sight operations, the airborne asset needs more than one communication network. Usually it uses common operations now is using radio frequency point-to-point between the aerial asset and the remote pilot, and having and providing that second communication bearer over satellite, for instance, or via cellular, may increase system redundancy and reduce also then reducing system failures, for instance, or may increase communications quality of service. You could use, for instance, depending on which scenario, you could use using satellite, because has a better, of course, maybe better coverage than in that case for a cellular, or and so on. And of course, having another communication beer may also provide a very important feature, which is adding air-to-ground and ground-to-air communication interfaces. And that eases coordination and operation with external, let's say, systems and services. For instance, one would be UTM, for instance, or via cellular, you can network operators can provide independent localization of area assets, for instance, for situation awareness or surveillance. So there are many aspects. And for instance, what's important, however, also from a commercial point of view, is, for instance, particularly for onboard connectivity, is the cost, size, weight, and power of these products have to be, there is a lot of room for improvement, because currently some of these products, particularly satellite, for instance, modems, are more targeted for more capable UAVs, but in order to provide that capability, then all these, let's say, characteristics have to be improved. Yeah, I think that's also, of course, then there's the operational point of view and also standardization, because usually if you use cellular or you use satellite, there are different domains, different worlds. So at the end, there is a regulatory effort and a standardization effort that those systems can be interoperable and is integrated on those platforms. Thank you.
Perfect. Thank you very, very much for the question and also the answer there. Thank you, Marcel. Okay, so coming into some of the questions in the Q&A panel, I've got one from Tim. How does the loss of EGNOS safety of live signal to the UK impact on your plans, as I see GNSS is at the core of your plans?
I can probably start that off if you want, Courtney.
Yes, please.
I think just to make sure it's clear to everyone else in the call, I think that what you're referring to there is that the EGNOS is, we're not technically subscribed to EGNOS anymore. So I think EGNOS is just one aspect of how we can use an enhanced GPS signal to navigate to an accuracy that might be required, but it's not the only way. And a lot of the work that's going on in other projects, but will relate to this project, is how we can navigate without the dependency on GPS. Clearly, the use of EGNOS is ubiquitous amongst general aviation traffic, particularly in Europe, and it is a a reasonable tool to use, but we're not currently using that. I hope that answers the question.
Brilliant. Absolutely. Thank you very much for that, Gavin.
Actually go on to say that from a regulatory point of view, we may need to have an additional non-space-based navigational system as a fallback. And there is research going on in alternative position navigation and timing technologies to support that as a fallback navigation process. So we recognise the issues with EGNOS, but you can't always rely on GNSS. So we are, as I said, looking at what is known as APNT as well.
Brilliant. Okay. Does anyone have anything else that they wanted to add? Brilliant. Okay. Phil Binks, this is a question for you. Altitude Angel states they support ANSPs, but no actual ANSP is a partner in this project. How will the collaboration with ANSP look like? Will partners such as Altitude Angel liaise between the project and airspace managers, or is there another way to ensure that ANSPs are not overlooked?
No, ANSPs are involved in this project. I don't know whether that person, the question is actually referring to NATS or not. So NATS are not necessarily directly involved in this project. But in the UK, there are what are the 65 ANSPs. The ANSP we've chosen is Cranfield. Cranfield have their own air traffic zone around the airport, have a flight restriction zone as well. So we are working with ANSP who manage the airspace. And the reason why Cranfield was chosen, because we're also using the NBEC corridor, and one end of the NBEC corridor is at Cranfield Airport. So airspace managers, it is absolutely critical we involve them. The project is all about operating at the very low level, so sub 500 feet. So we are looking at airspace managers who manage that portion of airspace today. At the moment, yes, it is only one ANSP, but we are learning. We're finding things out. And as when we move the project forward, we'll probably engage for more with other ANSPs. But they are a critical part and very, very important to get involved with this project.
Brilliant. Thank you very, very much. A question from James Campbell. May I ask why we limit the delivery payload of a drone to 3 kilograms? Duncan, you're on mute, sorry.
Thank you. I thought I'd press that button. Great. So yeah, thanks for the question. The use case that we defined was deliberately looking at the case of delivering to an end customer. And so the 3 kilogram payload was specified for kind of safety and just looking at the required size of a vehicle, the range, and obviously relating to the weight of the power source, the noise it would create, the landing space required, and so estimating that 3 kilos would be a feasible payload limit within kind of safety precautions. And it was also included an analysis of existing deliveries, in particular, where there is value in a rapid response delivery, and such as kind of the immediacy of a request to deliver within 1 hour. So yeah, we kind of just restricted it to a feasible 3 kilo payload, but that's up to review and obviously subject to regulation as well.
Perfect, thank you very much. Okay, and we have one more question. Well, we have a couple more questions, apologies. Have we considered bird strikes?
This is Phil. I think bird strikes, we haven't considered bird strikes specifically. However, detect and avoid capabilities are a bit of an elephant in the room. In that we need to establish a full detect and avoid capability, really, certainly to move into the wider airspace beyond the very low level. But it is still key to one of the operational needs to allow us to fly beyond visual line of sight. There are different ways of delivering detect and avoid, whether that's on the platform or whether it's a remote ground-based system. Avoiding birds is always going to be a challenge. I'm not sure that manned aviation has got it totally sussed, and drones are going to have a similar problem. But perhaps one might consider that drones, I would suspect, normally fly significantly slower than manned aviation platforms. So to some degree, I would expect the bird to get out of the way of the drone. I know you can't necessarily just go ahead on that assumption, but it's certainly a challenge that we need to consider and move forward on. So the answer is yes, but we don't have haven't reached a conclusion to it.
I can add a little bit more to that. So I think, you know, in the context of the what ifs, and bird strikes are very much considered in the basis of it's likely you'll have a structural failure, or you'll have a failure of a propulsion system or some of your subsystems. So it's very difficult to design smaller drones to withstand any of that. But at the same time, it's very difficult to design medium-sized or small to medium-sized aircraft that can survive bird strikes or survive bird strikes without too much damage. I know there's clearly a lot of work that goes into large passenger planes and their ability to ingest birds to a certain level, but it's not particularly not a particularly high in the horizon issue for the current work that we're doing.
Yeah, so something to add from my side. So that's from a sort of drone perspective from bird strikes, but from a traffic management aspect, in terms of the process of what drone traffic management needs to look like as an activity, it's one of the sort of the special circumstance or special cases that I think any traffic management capability needs to look at. If there is a bird strike and it's happened onto an air vehicle, regardless if it was drone or sort of piloted aviation. I think that still needs to be accounted for. And how do we safely alert and warn other users, what sort of things? So that's sort of the enterprise architecture aspect is considering, as an activity there, what is the what if scenarios? I mean, we won't be able to describe every possible avenue of these circumstances, but they would fall under a special circumstance where you'll need to consider a level of priority around what traffic management needs to deconflict, and also consider where they, to assist them to get safely back onto the ground, as it were. So that's what I'll add in terms of drone strikes from a traffic management perspective on there.
Perfect. Okay, thank you very much for answering that. On to a question from Matt Harvey. The CAA are the regulator. They are surely there and say so themselves to provide a service for the stakeholders, not the other way around. Phil Binks, did you want to answer this one?
Yeah, I'm absolutely correct. What we're trying to do with this project is we're trying to gather information, gather evidence about how to sort of move the industry forward. I think we're all in agreement that the drone industry is quite an immature industry at this stage. We're all pushing for what we call beyond visual line of sight activities. And a lot of work is going to be done to actually achieve that and to make sure it's regulated effectively. So what we're just trying to do is work closely with the CAA on this, to show them our findings, and from that, hopefully they'll be informed, or better informed, to start developing future regulation. But the gentleman's absolutely correct in what he says. But we're just, as a project, we are trying to move the drone industry forward. So we're trying to help each other out, I suppose, is the best way to describe it. I don't think one organisation can do it on its own. So it's a matter of all working together to move everything forward.
Absolutely. Thank you very much. Okay, I have a question here. Good morning. Thank you for such an interesting topics that were raised during the webinar. Indeed, it is a challenging problem, especially for the case of dynamic environment is involved. Probably this is already mentioned. I would like to ask to point to more details involved in the handling of faults occurring in platforms, how a fault may affect a swarm, or even the case of an intruder, how these can be addressed to guarantee safe operations.
I think automated prognosis and diagnostics aren't really a part of this program. But that doesn't mean to say that when you look at the build standards for the platform and the system, they aren't an important part. The CAA are in the process, as I understand it, of developing certification standards for drones in the same way that you would certify an aircraft or a helicopter. And these will come in for drones. Obviously, we've got a system of systems here, so the faults need to not only be, or fault handling needs to be not only on the platform, but in the communication networks and the ground systems. Perhaps the ground systems are more easily in that you can make sure you've got triplex and quadruplex systems because you don't have weight as a problem. Whereas the platform obviously is always going to have to try and minimize its systems to manage its efficiency. But yes, fault finding is something, and there have been previous studies done in other research programs to look at fault findings and prognosis and diagnostics, automated functions on unmanned platforms. So that work has previously been carried out. As far as intruders are concerned, that is a challenge, and it's something which is being looked at now. We all remember Gatwick Airport, I think it was 3 years ago, where they were seen as intruders in the airspace, which caused all sorts of problems. How do we do that? How do we manage that? I think that's down to the regulation, not only of the regulation of the airspace, but the regulation of the industry. And who can buy a drone, what that drone needs to be fitted with at a minimum before it can leave the shop or the station from which it's being delivered.
Can I just add to that about intruders as well?
Yeah.
I think the key to this is your surveillance centres established in a particular area which you're looking at. What we need to try and do is to obtain a single point of truth, which everybody can operate from. When you've identified, once you've got a single point of truth and you know who's playing in there, it then starts to become a little bit easier to identify that intruder or to highlight or to spot an intruder. If you don't have a single point of truth, then it's very difficult to know whether, putting into air traffic management terms, whether it's FDP, RDP paired. If you haven't got that pairing, you're now in trouble. That basically means it's the flight plan paired to return on your surveillance, on your situation awareness picture. As soon as that doesn't happen, then you can start introducing counter drone activities. And of course, they vary from place to place. And counter drone is something we're not looking at in this project. But to gain the single point of truth by deploying the appropriate sensors, I think are the only way you're going to identify intruders.
Perfect.
Indeed.
Okay. Yeah, absolutely. We've got it could potentially be a bit of a similar question. Is there any work on common standards for drones in terms of structural integrity and performance capability? Who will assess the continuing viability of operational drones?
I can take that one if you want. There is a lot of work going on in that area, and you can imagine there's several working groups across, FAA, EASA in the UK as well, and it's really one of the challenges is how you can map existing standards for manned aircraft onto smaller platforms, and it's relatively straightforward down to a point, but once you get down to what we might call smaller drones, something typically of the less than 25 kilograms, very difficult to get mapping across standards. But there are documentation, there are guidance out there are white papers out there. For example, the JARIS group, which has created the light unmanned aircraft standard. So there is work going on in that area, and it's really it's based on risk-based factors or specific risk factors. Most countries or most regulators work on this very much on a specific risk category or a operational safety case basis. But if we want to sort of move forward into how these things, how platforms can be certified, then you have to be certified against standard, and those standards are, I would say, in creation, depending which whereabouts in the world you are at this time.
The only thing I'll add is probably not to do with the structural integrity and performance capability, but we are considering as part of the sort of the regulatory theme and standards as part of this studies to understand the various communication standards, the interfaces between the drone and sort of traffic management capability. So I think that's an integral part, understanding that ecosystem. So there is something that we're trying to survey and understand what's out there, and then see how they all connect together as a sort of a minimum requirement to operate this entire ecosystem safely with the various contributing factors. It's not just about the drones, it's the whole piece of managing the airspace and the access to that. So it's something we are looking into as a similar thing around the standards piece.
Brilliant, thank you very much.